Hi, my name is Shashank. Our paper's title is Partially Supervised Novel Object Captioning Using Context from Paired Data. My colleagues Mahesh, Umesh and I at Intel were involved in this work. Let's start with a problem statement. Image captioning solutions describe salient visual concepts in a given image. These solutions require fully paired image caption data for training. Here is an example on the top right. However, these datasets have a limited number of object classes. For example, MS COCO dataset has only 91 classes. This led to novel object captioning solutions. These solutions caption images with novel objects. There are no paired image captions for such objects in the training dataset. Here is an example on the bottom right. Here bottle is a novel object that does not have fully paired training data. NOC solutions fall into two broad categories. The first category uses specialized model architectures which insert detected objects into the caption. The second category uses partial supervision. They use object detection datasets which can be considered as partially paired data. Our focus is on this category. We call our approach PSNOC, which stands for Partially Supervised Novel Object Captioning. PSNOC is agnostic to model architecture. We use partially paired data in two ways. One, we generate paired synthetic data before training. Here is an example where we generate synthetic paired data for novel object bottle. Two, we generate pseudo-label data during training. We use a three-step training process that uses fully paired data, synthetic data, and pseudo-label data effectively. This includes novel techniques like SCSTF1 and pseudo-labeling for NOC. The bottom right shows an example of caption generated using PSNOC, wherein bottle is correctly included in the caption. Here are some details on our synthetic data generation. We take fully paired data and use partially paired data to generate paired synthetic data. Firstly, on generating synthetic images. For each novel object, we need to identify the candidate object to replace in fully paired data. For this, we follow the procedure that is similar to previous work called FDM. We generate captions on partially paired data using a trained model. These captions are used to identify closest candidate objects to replace. For example, cake is a candidate object for pizza. Next, we need to identify the image pairs that should be used to generate these synthetic images. For this, we follow certain constraints. The novel object and candidate object's bounding box areas or aspect ratios should not be too different. Their object bounding boxes should not contain other objects. Also, consider replacing multiple objects in an image if the constraints are met. An example with zebra is shown on the bottom right. For synthetic captions, we directly replace candidate object word with novel object word. We also use simple heuristics such as removing color words, adjectives, or nouns within a certain word radius of the objects. For example, blue and frosted are removed in the pizza example shown on the top right. Our training process involves three steps. In first step, we train with fully paired data and generate a model. In second step, we include synthetic data and fine-tune the model. In third step, we generate pseudo-labels on partially paired data and further fine-tune the model. Here we generate two pseudo-labels per image, one that prioritizes novel object inclusion and the other that prioritizes caption quality. Typically, image captioning training is done in two steps. First, the model is trained using cross-entropy loss. Second, the model is fine-tuned using SCST. Here, model is directly optimized to improve the caption metric, usually CIDR. We propose SCST F1, a variant of SCST that also directly optimizes NOC metric. This metric is F1 score of novel objects. Images with novel objects are usually referred to as out-of-domain data. In SCST F1, the reward has three components: in-domain CIDR, out-of-domain CIDR, and out-of-domain F1 score. This optimizes both caption quality and novel object inclusion. Here are the losses we use in different steps during training. In step 1, we use cross-entropy loss. In step 2, we first use cross-entropy loss and then use SCST F1 loss. In step 3, we use SCST F1 loss. Here, we provide a comparison of our work with related previous works. PS3 also performs pseudo-labeling. They perform pseudo-labeling after each mini batch and maintain 2 copies of the model for efficient training. We perform pseudo-labeling after several thousands of mini batches and do not need to keep additional copies of the model, which makes our solution easier to integrate on existing models. We do not use any additional lexical classifier. Also, we generate 2 pseudo-labels per image as mentioned earlier. FDM also generates and uses synthetic data. They use object detection model to get region features in an image and then perform object replacement in this feature space. This restricts their solution to region-based captioning model. Our solution directly generates synthetic images, so it is more generic and not restricted to region-based captioning models. It also allows for human-in-the-loop data quality checks on this synthetic data. For synthetic captions, they train and use an additional scene graph-based model, while we use direct word replacement with simple heuristics. We perform experiments using held-out MS-COCO dataset that has 8 novel object classes. The dataset numbers, including our synthetic data, are shown in the table on the right. We use the popular bottom-up top-down model architecture in our experiments. We notice that SCST results in captions with bad endings. We perform post-processing to remove such endings. We call our solution without post-processing as solution 1 and with post-processing as solution 2. We use the standard evaluation metrics SPICE, Meteor, and CIDR on both in-domain and out-of-domain data splits. For out-of-domain split, we also calculate the macro average F1 score that evaluates novel object inclusion. The next few slides show our results. First, comparison with previous works. Our PSNOC solutions shown at the top outperform other related works on out-of-domain data. We get a CIDR of 103.8 and F1 score of 85.9 using our solution 2. We perform ablation studies to show that all the steps in our training help. This table starts from baseline solution at the top to our complete solution at the bottom, with ablations in between. Here are some qualitative examples of captions generated using PSNOC. For example, in the top right image, the caption correctly includes a microwave. Similarly, in the bottom left image, the caption correctly includes a pizza. In conclusion, PSNOC gives improvements over baseline and previous works. PSNOC uses fully paired data and partially paired data effectively. Our paired synthetic data generation is generic and not restricted to region-based captioning models. Our 3-step training process is effective and includes novel techniques like SCSTF1 and pseudo-labeling for NOC. Thank you.